And I am the man who does statistics because I can. And so I'm going to do a realistic example. We have 5 different kinds of metal, and we're going to make a door out of the metal and fire rockets at the door until it breaks. And these are breakable materials.
The metal is an alloy called adamantium, supposedly indestructible.
So each group has a different sample size, a different average, and a different standard deviation. Testing more than 2 groups means we're going to need to use ANOVA, and I can already fill in some of my ANOVA table. I have 5 groups. 5 minus 1 gives me 4. How many total do I have for sample size? 375 minus 5 groups is 370. Then 375 minus 1 is 374. Is it true that 4 plus 370 gives me the 374? Yes. Oh, good. Next, I need to know the overall average, and it's not told to me by default. I do have the average for each of the groups. How did we get that? We added up all the values and divided by n. So if I take this average and multiply by n, I'll get back the total for that group. Multiplying each average times the number will give me the overall total. And if I divide that by the total sample size, which I know is 375, that will give me the overall average of 17.2, which looks pretty reasonable if you look at this data. We couldn't just average these values because they don't all have the same amount of data. Here's a group that had a lot less data than the others.
Made of vibranium, the strongest substance in the universe.
So we have to do a weighted version like this to get the true overall average. Now to find the sum of squares for groups, we're going to use that 17.2, subtract it from each of the averages. So the first average minus the 17.2 and the second and the third always times that sample size to give us 64.7. That's what goes right up there. We're going to take each of these sample sizes, subtract 1, and then multiply it by each of the standard deviations squared for groups 1, 2, 3, 4, and 5. Add those up and we get 2257, which goes right here in the table. And you're thinking, that's a huge number compared to the 64. Yeah, but remember this is tempered by 370 data points here. So that 64.7 isn't going to be...
And he plays a lot of Minecraft where he runs a rather nasty mob.
What, is it zombie?
Zombie pigmen.
I didn't like how light-colored the green was, so I put in some blue on top of it. To get our sums of squares total, we take the sums of squares for groups and for error, add them together. We haven't really used this number yet, but hang on, we'll talk about it later. This is going to be the 64 divided by 4. Here, the 2257 divided by the 370, and that's why I said hold on saying how big it is. These values aren't as far off as you might think. Now let's pause right here and talk about this 6.1. If I take the square root, I'll get a pooled standard deviation, 2.47. It's in the middle of these, weighted based off who has more or less data. Now we're ready to finish our ANOVA table by taking the 16 divided by the 6. There's our F-score. That's the math part. Now we can do the rest of our hypothesis test, starting with our null hypothesis, which says all the metals have the same average. In other words, mu1 equals mu2 equals mu3 equals mu4 equals mu5. The alternative says that all the metals are not the same on average. And be careful here, there's a temptation to say they're all different, but they might not all be different. It might be that 4 of them are the same and it's only this one that's different.
Unobtainium, because this little gray rock sells for 20 million a kilo.
Or maybe they are all different, or maybe these 2 are the same and those 2 are the same, but the 2 are different from each other, right? Lots of different ways that could happen. So we just say not all the same, which is easier. We'll use a classic alpha, and our F distribution has 2 degrees of freedom, the 4 and the 370. The box up here and the box for error. And then the value is a 2.656. That's the hard part. That's why we spent so long getting the table before we even really started going through the hypothesis test. Now that we have that, all I got to do is go to the applet. We're going to switch to the F distribution, put in the degrees of freedom 4 and 370. And then put in my F value of 2.656. I want it to be shaded higher, and it's always going to be shaded to the right with a ANOVA table. The reason for this is because we squared everything, so the negative side of the tail flipped over to the positive side. So this actually is a two-tailed test, it's just both tails are on top of each other, and so it's always right-tailed to get that two-tailed p-value. That's why even though it feels like it's a two-tailed test, you don't need to double the p-value. It already did it. That's part of the shape of the F distribution. A small p-value means we want to reject the null, and that says the metals are not all equal. But who is different? Is it only one of them? Is it multiple? Maybe it's this guy.
Mithril. It was called by my forebears. No blade can pierce it.
We didn't test that. We can only say they're not all equal. So from here, you might want to do further testing to figure out which one is the best or which one perhaps is different.